So good day students, we'll be taking the next chapter 10, circles, and in this chapter we'll be mainly dealing with the definition of circles. As you can all see, a circle is a collection of points P1, P2, P3, P4, P5 and so on, such that which moves in a fixed distance from a fixed point. This fixed distance is known as the radius of the circle. OP1, OP2, OP3, OP4, OP5 and so on. So these points, they are the points in a plane which moves in a fixed distance from a fixed point. So this fixed distance is known as the radius of the circle, and the fixed point is known as the center of the circle. Next, we're talking about the tangent to a circle. As you can all see, a tangent to a circle is a line that touches the circle at only one point. Right here, line L is the tangent which is touching this circle at point P. Care must be taken that the tangent is a special case of the secant. Here the same line L is acting as a secant, but secant is touching the circle at two different points. Okay, so this line L will become the tangent when it touches the circle at one point. Again, you can see that I have taken a point exterior to the circle, and through this exterior point I have drawn two tangents, CE and CF. That means it is very clear that from a point, the exterior of the circle, at the most you can draw two tangents. So you need to remember that only one tangent is possible at a point on the circle. That means if you are drawing a tangent at point E or F which lies on the circle, or B, you can draw only one tangent, right? No tangent is possible from a point in the interior to the circle. Supposing if I take any point A, here I cannot draw any tangent, because as per the definition, tangent is a line which touches the circle at one point. At most, two tangents can be drawn from a point in the exterior of the circle. Just now I mentioned that, see here, the point C is outside the circle, exterior of a circle, and from this point you can draw maximum of two tangents. Here CE and CF are the tangents. Look, point number one, only one tangent can be drawn at a point taken on the circle. Now in standard 10 you got two theorems. You need to prepare those two theorems, right? And one of the theorem is generally asked in the examination for 3 to 4 marks. So I'll be discussing these two theorems one by one. The first theorem says that the tangent at any point of a circle is always perpendicular to the point of contact. Again I repeat, the tangent at any point of a circle is perpendicular to the radius through the point of contact. That means OP is the radius, right, and XY is the tangent. So XY is perpendicular to OP and P is the point of contact. How to prove this? Given, we are given a circle with center O and a tangent XY to a circle at point P. To prove OP is perpendicular to XY. Proof. You are supposed to take a point Q on XY other than P. That means on this tangent XY, you take any point Q other than P, right? And you are supposed to join OQ. Now the point Q must lie outside the circle, right? Therefore your OQ is longer than the radius OP of a circle. That means OQ is greater than OP. Since this happens for every point on the line XY except the point P. Now in 9th standard you learnt that the perpendicular is the shortest segment out of so many line segments that you take from a point not lying on the line. So you see that OP is the shortest side of all the distances. From O you can draw n number of line segments on this line XY, OQ, OM, ON and so on. So out of this, OP is the shortest of all the distance, right? So OP is perpendicular to XY. So you need to practice this theorem. The way of writing any theorem is, given, to prove and proof, along with the proper figure to get full marks. Next theorem. The length of tangents drawn from an external point to a circle are equal. So you have the figure like this. PQ and PR are nothing but the tangent segments, and you are supposed to prove that they are equal. And this is a very predominant question in the board examination. It is generally asked. As I told you, out of the two theorems, any one of the theorem may be asked, but it is been seen that this theorem 2 is asked on number of occasions. So we are given a circle with center O, a point P which lies outside the circle, and the two tangent segments PQ and PR. Our job is to prove that PQ and PR are equal. That's what we are supposed to prove. We are supposed to join OP, right? And by the very first theorem, you know that the tangent and the radius are perpendicular at the point of contact. So angle Q and angle R will be 90 degree each, right? Now you have to prove these two triangles. That means, see here, your OQ and OR are the radii of the same circle. So I can consider triangle OQP and ORP, these two triangles you need to prove congruent. So in these two triangles OQP and ORP, your OQ and OR are equal. Reason, they are red of the same circle. OP equal to OP common, right? And since this is 90 degree, already I have told that this angle Q, that is angle OQP and angle ORP are 90 degree, just because of the theorem 1. It's a right angle triangle. So by RHS test, the two triangles are congruent. Hence by CPCT, corresponding parts of congruent triangles, PQ is equal to PR. Very simple theorem. Sometimes this same theorem can be proved in some other way. Okay, this is the traditional way of proving, but some students do prove. What do they say? PQ square. In right angle triangle, POQ or OQP, whatever you call it as, you can apply Pythagoras theorem, where your OP is the hypotenuse in both the triangles. If you talk about triangle OQP or ORP, in both the triangles you will find that your PO is the hypotenuse. So I can say PQ square is OP square minus OQ square, and the same OP square being common can be written as your PR square can be written as OP square minus OR square, right? So your OP square minus PR square, as you can see, OP square minus OR square is nothing but your PR square. The reason behind, OQ and OR both are same, they are radius of the same circle. So OQ and OR, they both are same. OQ square and OR square will be same. That suggests that PQ square and PR square will be same. As PQ square and PR square are same, that implies that PQ is equal to PR. So this is the other way around. If you don't want to prove the two triangles congruent and then use CPCT to PQ is equal to PR, you can also use the concept of Pythagoras theorem in these two triangles, right? The way you can say that PQ square is nothing but PO square minus QO square, and your PR square is nothing but PO square minus OR square. Then OQ and OR you can replace it, and then you will get the answer, right? This way you will prove that the two triangles are congruent. Now remember that as these two triangles are congruent, I can very well say that angle OPO and angle RPO, right? They are nothing but you can say that OP is the bisector of angle OPR. That means your angle OPQ and angle OPR, right, they are the angle bisector. That is, the center O lies on the angle bisectors of angle, you can say QPR. That is, the center lies on the bisector of the angle between the two tangents. Thank you, children.